All right. Um, Today we're going to continue our discussion of electric fields and electric potential and all that stuff, but we're going to talk about capacitors, which is the new idea. I suspect that some of you have heard of capacitors or use capacitors or have some idea what a capacitor is, maybe from an engineering class. Um, but we're going to sort of talk about that in depth today. Um, Capacitor, the basic idea of it is something, some sort of piece of metal with a positive charge on it next to a piece of metal with a negative charge on it, such that there is an electric field from one end to the other. Um, these things are widespread in nearly all types of electronics. It's pretty common, and I'll get into what some of the uses are in a minute. There's basically two ways of using a capacitor. One is that you can connect both ends to a battery in order to charge it up. And the other way to do it would be to sort of trap charge on the plates. So if we were in person in the classroom, what I would do is I'd get out one of the capacitors from the lab, and I'd connect it up to this voltage source, and I would put a significant potential difference across the two leads of that capacitor, maybe something like 20 volts, and then I would disconnect it, like making it clear that this thing is no longer connected to the battery, and then I would take a paper clip and I put it on top of it and get it to spark, to prove that even though it wasn't connected to the power source, it still had charges trapped on the plates, an excess of negative charges on the one and a lack of negative charges on the other. And so it was able to hold that energy and that charge even though it wasn't connected to the battery. So again, there's two different ways to use a capacitor, either connected to a battery or almost like a battery itself, something that stores charge. So we'll talk about that in a minute. All right. If you connect it to a battery and you want to know what's the potential difference across the capacitor, well, that's an easy question, which is you look at the battery, or you take a multimeter on the battery and see what that potential difference is, and that is the potential difference across the capacitor. But if the capacitor is no longer connected to the battery, then it might be a little bit more complicated to answer the question exactly how much potential difference is across it, and we'll talk about those two different situations. So this situation is one in which there is no battery connected. This is not a battery, this is a multimeter, like the ones that we're going to let you guys borrow for the semester. This is a multimeter. It's measuring basically 60 volts potential difference across these two things. The idea is that negative Q worth of charge is trapped on this plate, and plus Q of charge, in other words, a lack of electrons, right, is on this plate. And so we can measure the potential across. Again, in this situation, the thing that is fixed is the amount of charge, because these multimeters are designed so that they can detect how much potential difference there is without like allowing charge to sort of leak from one side to the other, if that makes sense. They're very carefully designed to make sure that does not happen. Anyway, I don't know if any of you have ever been trained to do defibrillation. So that has a capacitor in it, as we'll talk about. My wife is a nurse, so she's had she's had patients go code blue, and she's had to resuscitate them, things like that. But if you watch the movies and you remember the part of the movies where they flip some switch and then there's some delay, and there's some like high-pitched thing, and then it's all charged up and ready to go to try to get people's hearts started back up again. The basic idea is that one of these ends is positive, the other one is negative, and so you're trying to get electrons to go like from this end to that end or vice versa. And by traveling through the heart, that should jumpstart the heart, is the basic idea. But what's interesting is that it helps if that jolt of electricity is as short as possible and as powerful as possible. And if you're going to do this using a battery, that limits how much time it takes, and the battery could potentially get really hot when it's doing that. But if what you're really doing is discharging two charge plates, in other words, this wire is connected in the box to two charge plates, then it doesn't matter how quickly the the charge is depleted, making two pieces of metal hot is not nearly as dangerous as making something that's immersed in like horrid chemicals. Like pretty much any battery that you can think of, if you were to break it open, do not try this at home. If you were to break it open, out spills incredibly caustic chemicals. And so if you make that battery super hot, that's going to be a bad day. So this is a nice way of getting around that constraint. So it's interesting because it's another example of the capacitor acting like a kind of battery, like a special battery that can discharge very quickly. So a capacitor with so again, that's another example of when we've charged at the plates, we've disconnected the battery, and then we're using the capacitor to do something. Now I'm going to switch gears, and I'm talking about what happens when you connect the capacitor to the battery. So here's a battery that is connected to a capacitor. You can see that there's plus Q and minus Q there. Again, the important thing in both cases is that there's no charge flowing across the plates. Maybe I should have said that earlier, but in this case, it's not the charge that's fixed. It's the potential difference that's fixed, and the charge will develop on the plates in proportion to how much potential difference that there is. So it's mathematically, it's a little bit different that way. Now, as you know, that there's a lot of devices that the wall electricity is not necessarily the same kind of current source that a battery is, but a lot of our devices will convert the wall to something that is quite similar to a battery. So AC to DC, we'll talk about that later. All right, so what I want to do is I want to relate that we want to figure out excuse me, we want to figure out how much charge develops on these plates depending on how much voltage you have in the battery. So if you have a car battery, I'm not as much of a gearhead as I should be. I can't remember if car batteries are 10 volts or 12 volts, but it's one of the two. And so if you have 10 volts of car battery, how much charge is going to end up on those plates? How much, what's the positive Q and the negative Q? It's going to be the same amount, but exactly what is that? So remember that because it's two charged plates and there's a uniform electric field in between the two, and we've been talking about this, that the potential difference is the electric field times the distance between those plates. That means that if you double the voltage, so in other words, let's say you connect two batteries to it instead of one, if you double the voltage without changing the separation between the two plates, that's going to double the electric field. What's interesting about that is the electric field is related to how much charge is there. Remember, this symbol is the charge per unit area. Well, if the area is the same, right, Q over A, if the area is the same, then Q has to double. So at the end of the day, if we double the voltage, for example, by connecting two batteries instead of one, which is what you're going to do at home, which is why we gave you 2 D batteries instead of 1 D battery. If you double the voltage, it should double the electric field. If you double the electric field, it doubles the charge per unit area. If you double the charge per unit area, that's going to double the charge. So at the end of the day, the voltage and the charge are proportional to each other. Okay? Again, if you triple the voltage, it triples the charge, so on and so forth. So you end up with this sort of proportionality where the more potential difference there is, the more charge there is. Again, this is the charge on, this is like the positive charge on the one plate and minus the charge on the other plate. So the more voltage you put on that thing, the more charge that you get on it. So this proportionality, so instead of just saying these proportional, we'll set them equal to each other, but define this capital C thing, we'll call this the capacitance, is what we're going to do. Again, this is the charge on the positive plate, the charge on the negative plate would be minus that. We have a new thing here, this constant, and so if we were to solve for C, we get something with Coulomb units divided by volt units. So we're going to define the units of this thing to be 1 Coulomb per volt, which is named after Michael Faraday. So we call it the Farad He's an English physicist. Michael Faraday is a fun guy. He used to do a lot of these like demonstrations in the 1800s. So he sort of was the first, like, you see people that are like I don't know, blowing things up with liquid nitrogen. He was sort of a popularizer that way. He was a pretty interesting person. Anyway, this sort of codifies this proportionality essentially. Now, the thing to bear in mind is that this is true as long as the size of the capacitor is not changing. Very rarely is the size of the capacitor going to be changing. If we hand you a capacitor, it's not like it's going to expand in size, and it's be very strange if like the material inside of it were to change. Like you might have some plastic in between the plates. It'd be very unusual to change that plastic from, PVC pipe material to Teflon or something like that. That would take a lot of effort to do that. So typically you don't have to worry about this capacitance changing. Typically the main thing that's changing is the voltage and the charge. We'll talk about, in the next lecture, we'll talk about sort of making things bigger, larger. How does that affect the capacitance? But usually we're not, usually things are just a component that's not going to change. That's, if we broke it open, it would stop working. So this is a little bit similar to how, this is an old school keyboard. So I'm told that modern keyboards do not work this way. But basically, if you have an ability to measure the voltage across this thing, and you can trap charge on this plate and on this plate, and in between the two put an insulator, maybe like foam rubber or something, and then you push down on the button, well, if you can measure the voltage difference across these things, this is changing the shape of the capacitor, so that actually does change the capacitance. The charge is the same, and so the voltage would be different, and so you can use this to try to detect if a key is pressed. So that again is the mode in which the charge is trapped, and the voltage is just whatever it is based on what that charge is. Now, every semester I've taught this course, I've seen students in the midterm do something like this, do something like that. So don't do that. Why are these wrong? Well, this I would say that both of these are wrong. This one is slightly more correct than the other one, because this one, if these were equal to each other, the voltage would be proportional to the charge. But in this one, if this was equal to each other, then the more the voltage, the less the charge is what it would mean. So this one is the worst of the two, but these are both wrong. Anyway. All right. So we've got some charge on the plates. And here's what we want to do. We want to figure out what is this C, what is this capacitance based on the size of the thing, if we just have two simple plates, two pieces of metal, one with plus Q, the other one with minus Q. So what do we get for C based on the dimensions of that thing? So the electric field from the two plates is the charge over the area. By the way, there's not a factor of 2 because it's in between the two plates. And so we can use that to try to figure out what the voltage difference is, right? Because the voltage difference is E times D. So we're going to use the electric field in just a second to do that. For right now, we're going to solve for the charge, right? So the charge is the electric field times the area times the electric permittivity. So that's the charge, and remember that the capacitance is the charge divided by the voltage, and so we can, so Q, remember the voltage is E times D, and so the electric field cancels out. We end up with the capacitance is E times A over D. You notice this does not depend on what the voltage is, which is sort of the whole point, which is Q equals C delta V. The only thing that's changing there is the voltage. The C is just a constant. And so if you don't change the area of your capacitor and the distance between the plates, then that capacitance is going to be the same. So that's our formula for what the capacitance is. And this sort of thing you could use with that keyboard key to try to figure out how much the voltage would change if it was pressed down, because it would change D here, right? All right. Now there's a lot of questions in the book that are similar in spirit to what I just did, except that instead of being for two charged plates, it might be for concentric shells, like there's a positive thing inside of a negative thing, and trying to figure out what the capacitance is there. So there's a certain amount of charge here and a certain amount of charge here. We're going to take the ratio of the charge to the voltage difference between the two and figure out what this capacitance is, that formula, based on the dimensions of the shell. There's a couple of examples like that in the book. And so you can do concentric shells. You can do, there's a positive thing, and then there's a cylinder outside of it. There's all kinds of problems like that. I personally don't think that they're super interesting, but I think that it's good to sort of look at what's there and appreciate that even though it's mathematically quite a bit more complicated than what I just did, it's still in the same spirit of saying, all right, well, our capacitance is something like this. Okay? All right. Now, capacitors appear in circuits, so it's important to talk about that. The capacitor symbol in a circuit, as many of you probably know, looks like this. It is no coincidence that this looks very much like two charged plates that are not actually connected together, and that's important because there is no way for charge to sort of jump from one side to the other. That is the key. That is one of the key properties of a capacitor. And so, sure enough, when they draw it, they make sure to show that the wire does not connect from one side to the other. It's easy to confuse this with a battery symbol. The battery symbol, if you look closely, one of the ends is smaller than the other, and often there'll be a positive and negative there. So don't get confused by that. You want to look closely to decipher the two. Now, this is how you would connect two capacitors in series. And what do I mean by series? There's series and there's parallel. What's the difference between the two? Well, this one is in series because the bottom of one of these capacitors, the bottom of this capacitor, is connected to the top of this capacitor. In other words, like the top plate. So, in bottom and top, what I mean by that? Well, the top plate is the one that's closest to the battery. So this would be the top plate of that one. This would be the bottom plate. So the bottom plate, and then there's these two plates here. Well, which one is closer to the battery? Well, starting from here, the one that's closer to the battery is this one, right? Obviously, this one is physically closer to the battery, but starting from this spot, this one would be more closer. So the bottom of this one is connected to the top of that one. When you are connecting things from bottom to top, that is a series. And so there's a variety of rules that exist in that case that we'll talk about. There you go. In parallel, that's different because now the top plate here, again, the plate that's closer to the battery, to the positive end of the battery, I guess, and the top plate here, the top plate is connected to the top plate, and the bottom plate is connected to the bottom plate. And that is what makes it not series. That makes it in parallel. That's the difference between the two. Now, what's nice about this is that when you're connecting it like this, there's a direct connection between this top plate and the positive end of the battery, and the bottom plate to the negative end of the battery. So if I wanted to know what is the potential difference across this capacitor and what's the potential difference across this capacitor, the answer for both those questions would be whatever the potential difference across the battery is. So this, in some ways, this circuit is a little bit easier to understand than the series one, as we'll talk about in a second. So let's see. So let's analyze this. So we've got some battery here, and it's important to note that these two capacitors are not going to have the same potential difference. So with the parallel circuit, they both would have the same potential as the battery. But this one, that's not going to be true because the potential difference across this plus the potential difference across this is going to equal potential difference across the battery in general for these circuits. So that makes it a little bit different. So we'll talk a little bit about that in a second. So just be on your guard that these are not going to have the same potential as the battery. Another interesting thing is that if you have the capacitors wired up in parallel, it's kind of like you have one big conductor with one big upper plate and one big lower plate, if that makes sense. That have like the same separation. And so you can think of like an equivalent capacitance from this thing like this. And you could say the equivalent capacitance would be something like, the total area divided by the distance across the plate. So if this is capacitor 1, this is capacitor 2. It would make a lot of sense if the equivalent capacitance was the total area divided by that, the distance between those plates, assuming it's the same distance. But in general, one finds something like this. The general rule is you just add it together. So this is true if the distance across the plates is the same. So this seems manifestly reasonable, right? It turns out that even if the distance across the plates is not the same, you still get just adding these things together. So this is for two capacitors. When you had multiple capacitors that were in parallel, the capacitance would just get bigger and bigger and bigger and bigger, it turns out. So I haven't provided 100%, 150% provided justifications for this rule, but I think hopefully I've convinced you that if the distances are the same, this is certainly what's happening. Now we're going to think about these series circuits again, and it's important to note that because there is no electrical connection from this side to this side, and from this side to this side, right? So there's no wire connecting one end to the other. That means technically this is an isolated piece of metal. And by isolated piece of metal, there's a couple things we can conclude from that. One is that there's really no good reason why this should be charged up at all. So the total charge on this isolated piece of metal should be 0. You might have charge on this plate and charge on this plate, but they should add up to 0, because if initially the circuit had this piece of metal was all charged up, it's probably about to explode. But under normal circumstances, there's really no good reason why this thing would be charged up. And so that gives us a relationship between the two plates, which means that minus Q here plus this should add up to 0, right? Because there's really no good reason why it wouldn't be initially neutral. And so if minus Q1 plus Q2 equals 0, that basically means Q1 has to equal Q2, right? Because this is the minus of that, so on and so forth. Means that whatever charge on this capacitor, it should be the same thing as this charge on this capacitor, even if the capacitance says they're not exactly the same. It's just and it all comes from the fact that this piece of metal is initially neutral. Now the voltages should add in series, because the way this thing is connected, so you're going through this potential difference and then through this potential difference, so it's you're kind of walking through the circuit that way. It would be rather strange for the total potential difference across this thing to be more than the battery that it's connected to. So in general, it's going to be those two things added together equal to the battery. And so when we think about what is the equivalent capacitance here, it's a little bit like this isolated piece of metal isn't really even here at all. It's kind of like this plate is the equivalent plate and the bottom plate is the equivalent plate. So we can work this out and try to figure this out. So Q1, there's a total charge on Q1. It's C1 delta V. Excuse me. And then Q2 is this thing over here. Again, what we want to do is we're going to figure out what is the equivalent capacitance. And so it's kind of saying what's the potential difference, what's the charge, basically. And so in a second, the following is going to be useful for us, which is that I hope you would agree that if you divide both sides by C1 and Q1, you get something like this, and the same thing over here. And so what we're going to do is we're going to take the fact that we know what delta V1 plus delta V2 is. We know that those two things have to add up to the voltage of the battery. And again, our goal is to try to figure out what the equivalent capacitance is. Which again is like, it's kind of like as if that piece of metal in the middle wasn't there. So we know the equivalent capacitance is you think of it as one capacitor with the potential difference of the battery that has a charge Q on it. But we don't actually know what this Q1 is just yet. So here we go. So the equivalent capacitance is the charge that's on this sort of equivalent capacitor divided by the voltage across it. The voltage across is just the battery. The equivalent capacitance, so the equivalent charge is just whatever charge is on that first plate. So we just say Q1, which is the same thing as Q2, but whatever. And so, again, we're trying to figure out what equivalent capacitance is, but what we really want to do is we want to figure this out in terms of the capacitances of the first and second capacitor, right? So now what we can do is we know that the potential difference of the battery equals delta V1 plus delta V2. And, you know, in the previous slide I had something useful for relating that to the capacitance. So what I'm going to do is I'm going to flip this thing. So 1 over CEQ gives us this. And then this gives us that. And then Q1 is equal to Q2. And so we find that this is equal to the capacitance, 1 over the capacitances, added together. Again, this all comes from, you know, understanding that the charge on the equivalent capacitor is just the charge on one of these plates. So the general rule is something like this for two capacitors. For more than two capacitors, you get something like this, and I think you can imagine what it would be for 4 or 5 or however many. But this is what you get for those rules. Now, let's see. So just to review kind of what we've talked about, when you have two capacitors in series, it's important to remember that the charge on this one is the same as the charge on that one. There's no way around it. So I think that's what it says here. The charge on the equivalent capacitor is just the charge that's on one of the plates. And the voltage drop across this one is probably not the same as the voltage drop across that one. Now, why do I say probably not? That seems to imply that there is some situation in which it would be the same, but maybe not in general. So why do I say probably not? Well, if the capacitances were the same, then yes, the potential drop would be not. If the capacitances were the same, if C1 equals C2, then the potential drop across each one would be the same. Of course it would. But in general, C1 is not going to be exactly equal to C2, right? So the potential drop is not, in general, going to be the same. If you have, again, just to review, if you have two capacitors in parallel, the charge on this capacitor and the charge on this capacitor is probably not the same. We know the potential drop is the same because of the way that's wired up. We know the charges are probably not the same. We know that if we had an equivalent capacitor for this, it would be Q1 plus Q2 because it would just sort of have one big top plate is basically the idea. Now, why is it probably not the same? That seems to imply that there is a situation in which it could be the same. And yes, so if C1 was equal to C2, then yes, in principle, the charge would be the same here as the same here. But in practice, capacitances are never going to be exactly the same. And so that's the caveat there. All right. I think I'm going to pause here, and I'm going to record this later, but hope this is useful so far.